All right, thank you. My name is Michael Armella. I'm a senior data engineer at Credit Karma. So at Credit Karma, we provide credit reports and credit help for over 80 million members. And what I work on is the recommendation system. And what we're doing is providing credit products and advertisements on the site for our members. And what I want to talk about today is the danger of implicit blocking in Finagle. So Finagle is an RPC system written in Scala, and it's designed for high performance and concurrency, and it was created by Twitter. And we use this as part of our servers and client architecture. I hope everyone should read this blog about Block Party that Twitter came out with, and it really explains what the problems are with blocking and why it's such a big problem. So there's two types of blocking. There's explicit blocking, where you call Await.result or Await.ready, and this will completely stop your thread from doing anything except for waiting for the result of the future that was called. But there's another type of blocking that happens, and it's when your code runs some synchronous operation that's doing a computation, and it's waiting for it to finish. So this would be like running a very long computation or doing something that doesn't return right away. So something like calculating a factorial or some other mathematical operation would be a good example of that. So I'm going to talk about what happened and what our problem was. So we have a service that's consisted of multiple Finagle services. So each one of these is a Finagle service that's running on a separate machine. Some of these services are fronting MySQL instances, another is fronting an Akka cluster, and another is fronting a big table instance, a Google big table instance. So we have the orchestration service, which actually takes in the request, and then it will in parallel call the configuration service and the data retrieval service. And then it will pass this information on to the data processing service, which will do a long computation, and then to the ranking service. Well, what we noticed is in testing, in our staging environment on very low load, there were no problems. This ran in like under 200 milliseconds, everything was good, and we deployed it in production. As soon as we saw peak load times, we saw lots of problems. So immediately, the latency jumped up, and sometimes it was up to 10x, taking up to 2 seconds to process a request. And so why was that? It was because somewhere in our data processing service, we were actually running a long computation directly in the apply method of the Finagle service, and this stops it from being able to properly respond to requests. So let's take a look at a simple service with no latency problems. So this should be a boilerplate service that everyone who's familiar with Finagle should have seen. This is basically just creating a new service. It runs in constant time. It has a constant response. The only time this would take would be the network time. So what if I change this to actually compute something? So here we have an Await.result. Does anyone know what happens when you do this? Anyone? So this will actually run very badly. So when I call Await.result and then I sleep, it's going to sleep for 1 second. And it's going to completely stop responding to requests for that 1 second. But let's change it to do something else that's more sane that someone might actually do. So that previous example, I hope that no one would ever do that. But someone might do this. They're writing a service, and then they write some function, like calculate the Fibonacci sequence. And they say, give me the 100th Fibonacci sequence and return that as my response. So does anyone know what happens if you do this? Who thinks this will perform better than the previous example? Who thinks it will perform worse? Yes, this will actually perform worse, or at least just as bad. So what's going to happen here is this is going to start calculating this Fibonacci sequence, and it's just going to block just like the other one did, and it's not going to have any way of responding to new requests. Let's take a look at another example where not only am I calculating the Fibonacci, but I'm actually making an outbound request at the same time, or just previous to it. So this should be fine. It should seem like this client request should go out It should run asynchronously on the other machine, and then I should be able to calculate Fibonacci on this machine. But when you actually run this, it's actually going to be worse. And so the reason why it's going to be worse is because when you're blocking and you're wasting all of your threads time calculating Fibonacci, it can't actually make the request call. So when you have a very high load on your machine, when the new request comes in, it's going to try to make a request out, and the request it makes out is going to be using a similar thread that is actually processing Fibonacci. So the reason why this is because underlying Finagle is run on the Await.ready framework. So the Await framework is the NIO framework that is used by Finagle to handle all of its I/O operations. And what's going on with that is that every I/O channel has its own event loop. So the event loop for incoming requests is on the left, and on the right are all the outbound requests, so every client your service connects to. And they all have one central worker pool. So when an event comes in, a request comes in, it will get picked up by a worker thread, and then it will be processed, and it will try to make a callback. It will also, those same threads will make an outbound request on the event loop on the other side. So what happens is Finagle expects your service to immediately return a future, and it will register that as a callback. If you don't immediately register a future, you're wasting a worker thread that cannot respond and pick up a new request off of the stack of the event loop. So a good analogy of how this works is it's like a switchboard. The operator receives your call and then immediately tells you to hold and transfers you to someone else. In this example, the switchboard is your event loop, and the operators are your worker threads. So what's happening is, like, imagine if one day on the switchboard, they tell them, instead of when someone asks for their bill details, don't transfer them to the billing department, just calculate it yourself and tell them, even though it takes a minute or so. What would quickly happen is, under peak times, all the operators will be busy calculating this bills and telling the customers, rather than transferring calls. And eventually, there will be no operator available to actually transfer calls. So, and what happens when you actually block? So what's supposed to happen is the worker thread is supposed to register a callback immediately. So it's supposed to just take the request, start the asynchronous work, and return that as a callback. But what happens if you don't do that, and instead you're just busy processing some computation? You're not returning back, and there's no one picking up the new request off the event pool, the event loop. And so if this happens, then more and more requests just sit on the event loop and not processed, and it causes a lot of problems. And the number of workers is, by default, limited to 2 times the number of logical CPUs, which would be the cores of the machine. So the easy way to identify this happening is to look at 2 metrics that Finagle provides. That's blocking MS and handle time microseconds. So blocking time MS, it tells you when some part of your code has explicitly called Await.ready or Await.result. So if you see this time at all in your code, it means somewhere there's an await that's actually blocking your code, and you should really find it and remove it. But handle time microseconds will always exist in a small amount, and it's the time it takes for a request to come in, a future to be chained together, and returned back to the caller. So there will always be a small amount of this, but if this is growing very large, it means you're not responding to the request fast enough, and you're not building your future chain fast enough. And you need to debug why this is happening. Another problem to look out for is this does not just affect you processing inbound requests, but it also affects you processing outbound requests. So if you want to make an outbound request, you're using the same thread pool. So you won't actually even be able to queue up an outbound request if all of your threads are taken. So how to solve this problem? So the problem isn't just that outbound requests are bad. Everything is fine when we make an outbound request. It is perfectly asynchronous, but you need to minimize the code that is actually doing work inside your apply method that is not asynchronous. You need to avoid using await, and you need to run your code in a separate future pool. So future pool is what is the thread pools, how they're implemented in Finagle. So let's look at an example that doesn't block. So in this thread, in this service, all I've done is I've wrapped the previous one in a future. Who thinks this will perform correctly? Does anyone think it will perform correctly? So what, does anyone know what the problem with this is?
A limited number of new threads.
What?
A limited number of new threads.
It's not, that's not actually the problem.
We need to indicate that this is a blocking operation.
No, so.
I think it just immediately evaluates, right? It's a future.value, right?
Yeah, so the question you should be asking is what type of future is this? This is not a Scala future. In a Scala future, this will automatically run in a new thread. In a Twitter future, this will run in the same thread that spawned it. So this is a very big difference that a lot of people don't realize between Scala threads and Twitter threads. So this will do nothing. You're basically just wrapping a constant operation with a future in the same thread. The proper way to do it is like this. I initialize a new future pool, and so this is basically a new set of threads, and then spawn the future. This code I wouldn't say is very production ready because it does have an unlimited number of threads, but it's much better than the previous code. So now if we do this for our previous example, what's going to happen here is I'm going to spawn two asynchronous operations, and then I'm going to map on both of them. So this will run perfectly fine. But there's one catch that when you do the mapping at the end, where I have response.setContentString, what's going to happen here is it's going to return back to the initial thread. So if you do a lot of work and when you map on the threads in your apply method, that is also going to block. So be careful with that as well. So basically, in conclusion, latency problems are not always obvious. There's sometimes hidden things that you don't know about going on in your system. You should always investigate why you're seeing these weird latency problems. And you need to pay attention to the metrics, especially handle time microseconds and blocking MS. How you execute your long-running computations really matters. You always need to run them in a separate thread pool. And this is implemented in Finagle with the future pool. So the best way to do this is to actually tune your future pool to be the size appropriate for your architecture and your machine. And that's about it. Thank you. Any questions? Yeah.
How do you select the bounds for the threads?
How do you what?
How do you select the bound for the thread pool?
So it's basically more memory dependent. So if you use the unlimited thread pool, what's going to happen is if your requests are coming in faster than you can process them, you will essentially make an infinite number of threads and you'll fill up memory and you'll run out of memory. So you need to balance out when you're going to basically start rejecting requests or slowing them down and delaying them.
What profilers do you use for that?
You could use like the basic JVM profilers and things like that. Because this is all running on the JVM, so everything the normal JVM profiler would tell you. Any other questions?
Are there any like static ways to check your code to see this work, or do you have to basically profile your code?
No, so there's no, like I said, when you compile this, you won't see it. When you run it under low load, you won't see it. It only kind of appears when you have a very high load. So it's very difficult to statically check this. Yeah.
Do you have preference for load testing libraries? That's
I don't have any preference. I usually use like artillery or things like that are things called Gatling that actually will put a heavy load. Using these will really show you what your system looks like under load, at least in your staging environment. Okay, no more questions? right, thank you.